Now, line defects. So we're up to one-dimensional. These are also called dislocations, and they're a linear array of imperfections. So the point defect was a single atom, a single ion, a single imperfection. Now we have a whole row of them. We can have edge dislocations, we can have screw dislocations, and mixed, which are a combination of edge and screw dislocations. So an edge dislocation is where there's an extra half of a plane of atoms in the lattice. So, you look where this dark line is going through the matrix here, and below it there are only 5. It's a 2 by 5 grid. Above it is a 2 by 6 grid. There's an extra half of a plane. There's an extra row in there. Right above that dark line, where it transitions from 6 to 5, there's a lot of strain. There's a whole line of defects. A screw dislocation is when you still have 5 long and it's still 2 wide, but it's offset. So you're kind of getting a screw pattern. At the bottom it's a nice rectangle. At the top it's offset. So clearly this is an imperfection. It's not a nice regular lattice, and it's causing strain within and stress within the crystal. And if you can extrapolate this out to much larger, you can see how it's a very imperfect crystal. Now, the cool thing is these are first of all, they're incredibly common, and they can be incredibly beautiful. This is what leads to crystal twinning. This is how we get these, cubes of pyrite interlocked with each other. It's how we get these different crystals of quartz and tourmaline, and I don't even know what all of these are. We've got fluorite, and I'm not sure. But I picked these because they were really gorgeous. Some of them are very rare minerals. So, not all defects are bad. Sometimes we want defects in our crystals because it can be beautiful. However, when we're talking about plastic deformation or ductile deformation, we're talking about the negative effects of these imperfections, allowing the rock to deform. Now, to measure it, there's something called a Berger's vector. This tells us the amount and direction of dislocation within that crystal lattice. To do it, when we've located an imperfection, we look at the lattice and we start at an ion or molecule, depending on what kind of crystal it is, and we follow a path that should make a rectangle. So, if we go up 5, over 5, down 5, and back over 5, if it was a perfect crystal, we'd be exactly where we started. Now, it could be up 20, over 5, down 20, and over 5. Again, it's something that should make a rectangle. If there's an imperfection, it's not going to work. You're going to end up in a different atom or molecule than where you started. For example, here's a crystal lattice, and there's an imperfection. It's a line imperfection right through the center. Now, if we start somewhere, right here where it says start, and those are all 6 ions long, it did not end up where it began. is offset by 1 to the left. So our burgers vector is length 1 and it's to the left. On the other hand, here's a dislocation, and if we start here, go over 2, up 6, over 2 more, down 2. I'm sorry, it was up 8, over 2, and over 2 more, down 8, and to the left 2. We're not where we started. We're directly under it. So our burgers vector is 1 pointing up. Now, burgers vector isn't always going to be 1, depending on what's going on. It could be 2 or 3 or 4. It could be at an angle. It could be up, down, left, right, forward, backwards, any direction.